We're back. Just one quick thing on housekeeping. There's going to be a 30-minute break after this talk. You'll probably need one. And coffee and whatnot. So without further ado, I want to introduce Stefan Lauwawade. That's how you say the name. He is Mr. STL, literally.
So yeah, I'm an STL maintainer. I work with Dinkenware to maintain Visual C++'s STL implementation. Before we get started, I want to explain the title of this talk, Don't Help the Compiler. This comes from something that our front-end developer, Jonathan Caves, who's with us in the audience, once said to me. This was like years and years ago. We were looking at some incredibly wrong user code. Code that comes into our offices is often not healthy. And I forget exactly what it was, but he said something that seemed funny but cryptic to me at the time. And he said, these users, they just should not help the compiler. They'd just be so much better off. And yeah, at the time it made sense to me. But in the years that followed, as I saw more and more examples of users just injuring themselves by trying to help the compiler, I really gained an understanding of what he meant. And that's influenced the way that I write code and how I suggest to other people how to write their code. So that's what this talk is going to be about. So I'm going to blast through this about 30% of light speed. I'll have questions at the end, hopefully. If you're confused about anything, write down the slide number so we can come back to it really quick. I find that to be extremely useful. So first off, as programmers, what we're doing is we're writing text files that speak to other programmers, but also to the machine. And the machine is very different from humans. Okay, as humans, we have high-level understanding of what our programs do. We know about invariance. We know about the overall goals of the program, what is correct. The machine doesn't care about any of that. It just sees bits. It's going to add some bits, XOR some bits. But it's not entirely dumb. Although if you read like template error messages from the STL, you will be convinced that the compiler is dumb. It's not dumb. It's just very limited in what it understands. The compiler actually sees every single line of your source code every time you compile it. It sees every sub-expression. It actually knows a lot of stuff, what I refer to as low-level information. It knows the lifetimes of every object in your program, when to construct things, when to destroy things. As we've seen in the previous talks, especially Bjarne's, this is extraordinarily powerful. There's also this notion that until recently I was saying was called L-valueness and R-valueness. Then I looked up in the standard. There's actually a name for this. It's called value categories. I learned something new while writing this. And this is a sort of nebulous thing in C++ 98 that is much more concrete and crystallized in C++ 11. And this is whether expressions refer to objects that somehow either the rest of the program can see or won't see, and so nobody will mind if we go, steal its brains and take everything that's not nailed down. This turns out to be extraordinarily useful information, and C++ 11 gives us the tool to work with this. And then finally, there's this notion of types. So if you go back during C and C++'s development, we started without a type system. If you read how DMR developed C, he started with B. B is no type system. It's like, hey, here's some bits. I'm going to treat them as floating point. OK, now I'm going to treat them as integer. And the type system was then grafted onto this very low-level notion of a machine. We've lived with types for so long, sometimes we forget what they're doing for us. We fail to appreciate what they're doing for us. So they encode at compile time what can be done to an object. For example, vector has the array index operator, but it can't splice. And list can splice, but it can't array index. But it's not just that. It's not just, yes, you can do this, no, you can't do this. It also, the type information that's flowing through the program controls what the source code does. For example, if I've got the expression a plus equal b, well, that means addition for integers. I have to go see, OK, a is an int and b is an int. But wait, what if a and b are strings? Now that means concatenation. That's a function call. That's totally different. Or it can mean something else. What if they're atomics? This means atomic addition. That's a totally different instruction on the machine level. Yet it's the same source code every time, a plus equals b. The effect that it has is controlled through the type system. This is OK. Yeah, you can overload operators. And this is not specific to operator overloading. This is specific to functions that are overloaded or templated on types in general. And the types are one input to the equation. The other input is your source code. The compiler knows the types. You write the source code. So you have a high-level understanding of what your program does. The compiler is tracking all this stuff. So my talk is going to focus on these three different things. It's not an overall overarching view of here's how to write good code in C++. There are certainly things that fall outside these three domains, but I find that these three domains illustrate the principle of don't help the compiler. But of course, C++ is not a static language. It likes the keyword static, but it is not itself a static language. It is growing and improving over time. So in C++ 98, we actually had very primitive methods of working with lifetimes. We had autoputter, which is grayed out because it's horrible. That was a way to own a single dynamically allocated object. Not everything was horrible. We have vector, and vector is seriously my favorite type in C++. It is so awesome. I was extraordinarily pleased when I saw Bjarne's talk saying, if you know int and vector, you know C++. I totally agree with that. But then in C++ 11, or sorry, in TR1 in 2005, so halfway in between, we gained shared putter from Boost. And this allows us greater control over lifetime. It says destroy this object when all of the shared owners are destroyed or reset or reassigned or so forth. Then in 11, we gain make shared, which completes the shared putter equation. It offers control over the construction of the object in addition to its destruction. And we gained unique putter, which says, OK, you can only have one owner of this object, and you can move the owner around, but you can't share ownership or anything like that. And then in C++ 14, we finally got make unique, which again completes the construction side of the equation. As far as value categories go, the major improvement here was, of course, in C++ 11, we gained move semantics and perfect forwarding, which allow you to either steal resources from R values, as we've all been trying to learn, or accept arbitrary stuff and pass it to something else, and keeping all of those bits intact. So if they care about L values or R values, that information is preserved. We even have things like ref qualifiers, which allow member functions to ask, am I being invoked on an L value or an R value? And in certain cases, you actually do want to constrain or somehow switch on that bit of information. And then as for types, as I said, it's really easy to forget all the stuff that's doing for you. But in C++ 98, we had both overloads and templates. And these are extremely powerful features. Imagine living without overloads and templates. I mean, just go back to programming C. Ugh. What these do is, based on the type information, they allow you to select a different function. If you go look at C, just for its square root or absolute value or whatever functions, they have to name them differently to work on floats versus long doubles versus doubles. And in C++, you just call the function with its plain name, and it overloads, switching on at compile time the right function. And that's zero overhead, because you get inlining. All of that happens at compile time. You're not paying virtual function calls. Same things with templates. You stamp out an instantiation that depends on the types, but you're not paying virtuals. You're not doing any of that stuff. So that's very powerful. In TR1, even though it was a library-only extension, we gained more subtle ways to work with types. We gained stood function, which allows you to do something absolutely magical, and you do not ever want to have to write this yourself. It allows you to take a function object, a functor, and erase its actual type and preserving only its signature, like the Cheshire Cat disappearing but only its smile. That is a very nifty trick. Now you can have containers of stood functions and yet put arbitrary functions and replay actions later. You couldn't do that in C++ 9803 without writing that technology yourself. Or type traits. Now we can ask, hey, is this type a reference, or is it counts qualified, or is it an enumeration? What is the underlying type of this enumeration? All of these sort of fine-grained questions, many of which cannot be answered without the compiler's help. And TR1 gave portable hooks to ask the compiler these questions. And of course, the compiler knows. It always knew what the underlying type of an enum was, or whether a type was floating or integral. And now we can ask it these questions. So in C++ 11, they added a lot of machinery to manipulate types. We have auto, which says, make the type of this thing the type of its initializer. You couldn't do that in C++ 03, even though the compiler always knew the type of the initializer. Or decal type, which is even more hilarious. In C++ 98, if you're a library programmer, you know what I'm talking about. You just could not ask the question of the compiler, what is the type of this expression? Of course it knows, and if you pass it to a function template, it'll give you the type there, but you can't get it out at the higher level. Decal type lets you do that, and we're going to see an extensive example of that. Lambdas, I also count this feature as working with types. They don't really inspect type information, but they allow you to create novel types and an object of that type very, very easily in your source code. And so now you can just give lambdas to function templates, which care about type, and that information propagates through the system. So even though it's not technically allowing you to do anything completely novel, you could always write functors by hand. In effect, it's so much easier that it is a new ability. Null putter, we'll see how that propagates throughout the type system, and variadic templates. In C++ 03, we could only work with a fixed number of types. Now we can write things that process an arbitrary number of types. We can count above 5 or 10, say, which is useful. And this is going forward. In C++ 14, we have generic lambdas where you can say this lambda just accepts arbitrary stuff, and it's going to have a templated function call operator. Or you can give ordinary functions the same trick that lambdas got in C++ 11 and get automatic return type deduction. The compiler knows your return type. You say return expression. It knows that type. Yet you have to repeat it up at the top of the function because that comes first. Now you don't with return type deduction. We'll see an example of that. So not everything falls into these categories. For example, raw string literals are extremely fun. You can use them with regexes and HTMLs, but they don't really fall under the banner of lifetimes or valid categories or types. So this is not like everything fits in these categories, no. But many features do. I find it a useful way to look at the language. So what I'm going to do is I'm going to show you many examples of bad code. Code that I've actually seen in the real world, often through Visual Studio itself, that we've broken in various ways updating the STL, most of which were caused by the standard itself, not just us gratuitously breaking things. So it's going to have examples of things not to do, which is useful. I'm going to show a bunch of new features from all of and I'm going to cover all the standards, 98, 03, 11, and 14. Yes, there is something 03 specific. It's very subtle. But most importantly, what I'm going to try to do is try to give you a new ability to look at code and see something extra, which I have not seen at least clearly described before. So let's start. Lifetime. So I'm going to show examples of bad code. There's too many of us to do like interactive Q&A, and I have way too many examples. But I'd like you to raise your hand if you see what is wrong with each example. So if I see lots of hands, then I'm going to know, OK, everybody sees what's wrong, and I can go fast. But if I see very few hands, I'm going to know that it's confusing, and I should slow down a little. OK, they start off really simple, and then they get complicated. Then they'll get simple again in the next example. This is the simplest example in the whole talk. Here I've got some strings, meow, purr, completely random words. And I want to concatenate them with commas. Put the meow first, put the purr second. One is a std string. One is a const-char star. So I want to concatenate them. I saw a user actually doing this. So they know that std string has an operator plus. So they say, OK, string stir plus string comma, all that stuff. What is wrong with this code? Who sees what's wrong? This is like C++ 98, like every beginner should see this. I need more hands. OK. The problem is that they are constructing temporary strings for these concatenations. They do not need to do this. Strings operator plus is overloaded for std strings on the left and const-char on the right, and vice versa. And now with R value references, almost all of this is unnecessary. So for the foo call, if the user just wrote stir plus comma plus putter, it would compile and it would be more efficient. They would construct fewer temporary strings. The one where a temporary string is constructed from stir is especially gratuitous because it's already a std string. I mean, come on. And yet I saw someone writing this. That's completely unnecessary. Now, not all of them are for something that's kind of a headache relating to how string is not a built-in type in the language. In the case where on the left-hand side you start with a const-char star, and then the other thing is not a std string, but it's like a string literal or another const-char star, you can't add those because operator plus is left-to-right associative, and we can't overload built-in operators. So there you actually do need to introduce the type std string to pick up the right overload, and then after that you'll be OK. You could alternatively use parentheses to make the right-hand concatenation happen first, but that would be weird. I would just say string there. And you could put this either on the putter or the string literal. Either's fine. I would put it first. It actually gets better in C++ 14. You can write fewer characters, because in C++ 14, you could say, oh, let's make that comma string literal a std string using user-defined literals in the standard library. That was voted in to the working paper, I think, at the last meeting. So when that's implemented, you'll be able to do that sort of thing. But you still need to introduce the type there. After that, let the compiler take care of constructing those temporaries. It knows when to based on the overloads. And sometimes it doesn't even need to construct temporaries at all. OK, so vector string insertion, almost as simple. I still expect to see a lot of hands here. Here's some code where I've got a vector string. I'm pushing back various things into it. I want to push back meow, and then meow purr, and then kitty. These are following a certain theme, and then just some empty string for whatever reason. So what's wrong with this code? Who sees? Okay, yes. It may be that I'm constructing too many temporary strings again. And yes, that is the answer. So again, the case of pushback, string stir, especially gratuitous because it's already a stood string. Same with stir plus per because that operator is going to return a temporary string. In these cases, we should absolutely be calling just pushback stir and pushback stir plus per. Here I've noted on the right-hand side what overloads these are going to call. So instead of redundantly copy constructing or move constructing a temporary string and then destroying it, these will directly call the overloads that copy a new element or move a new element, and you're done. That's the best you can do. In this case, we really do need to copy or we really do need to move. We can't get more efficient. However, it's not the case that you can simply, or that you should simply, remove the temporary strings from each one. For the pushback of a string literal, yes, you could remove the temporary string there, and that would be good because you would get the pushback tref called. However, you would be constructing a temporary, moving it in, and then destroying the temporary. And like Andre said, what's better than some code? It's zero code. If you instead say emplace back with the string literal, this is a new C++ 11 feature that allows you to directly construct an element in your vector from the provided arguments. You literally cannot get faster than this because you're omitting 0 wasted instructions. So from a string literal or from no arguments, you can just emplace back with that. It's less typing and it's more efficient. So you shouldn't be trying to help the compiler say, here, generate a temporary and then push it back in. Just call the right overloads of vector and allow it to do that work for you. So my recommendations are you really don't want to be writing explicit temporaries in your code more than necessary. In fact, if anything, C++ really enjoys creating temporaries. It wants to create temporaries all the time. Don't help it further in that regard. You should be asking, I've got some types here. Can the compiler just use them directly, like in the case of strings operator plus, taking a stood string on the left and const char star on the right? If so, definitely don't create extra temporaries. Or sometimes the compiler can't work with your original types, but it can implicitly construct a temporary, and that's the best you can do. I see this all the time in cases where something is, say, returning a stood string, and the function, they need to return like a string literal or something, and the user says, return string paren string literal. Why? If you just returned a string literal, then the compiler would construct that return value for you. Now, that's not to say that temporaries are always wrong. If neither of those things are true, the compiler can't use original type and it won't implicitly construct a temporary, then feel free to write your own. For example, if you need to hash a string, a member string, you can create a temporary hash functor. It's stateless. That's not going to cost anything. There's other cases where you'd want to write temporaries, but try to avoid it if possible. Otherwise, you're just going to make more work for yourself and for the compiler. Specifically for the containers, there's one school of thought that says, oh, now we have emplace back, and yeah, for backwards compatibility, we need to keep pushback. So we should just use emplace back whenever possible in new code. And I can't exactly argue with that rule, but I'm sort of not completely in the 11 mindset yet. My guideline is that I prefer to call pushback when I'm starting with the type already. So if I've got a vector of string and I'm starting with string L value or R value, I will call pushback because emplaceback won't buy anything extra. It's already of the same type. You can't do better. I'm sure that Scott will be mentioning, oh yeah, for braced init lists, you also need to call pushback. Yes, he's right, and for a few other things. But aside from those squirrely little bits that can't be perfectly forwarded, if you're trying to push back something that's a different type, or you would prefer to construct the object from 0 arguments or 2+ arguments, then pushback is not ideal. You should go directly to emplaceback. Just say, construct this thing in place. It's a placement new. And that's less typing, and it's more efficient. And it can also invoke explicit constructors. So the constructor being explicit is not a reason to avoid emplaceback. OK, so I've been showing lots of examples with strings and meows, and I'm going to go right back to that. But in this presentation, I've got one realistic example. Yeah, it's like a dozen lines. And we work on code bases that are like, 10,000, 100,000 lines. This is not a lot of code. It's just slides are very small and difficult to convey complicated code. This doesn't even have any branches other than the if tests for errors. So here I've got some actually realistic code that's using libping 1.6's simplified, this is the simple version, API to decompress an image into RGBA format and upload it to a texture somewhere, and then we're done with it. Upload text or some other function. So this code, it will compile, it'll work, but it's wrong. What's wrong with it? Who knows? Who can see what's wrong? Okay, I got a few hands. I know it's a lot to digest. This is basically saying, and I should actually walk through what this is doing. This is saying, let's construct a ping image IMG on the stack. This is some POD. It's provided by the library. It's a C library, so this isn't going to do anything fancy. We need to mem set it to all bit 0 because the API tells us, and then write in a constant because the API tells us. Then we can call a function to read the header and figure out how big the image is going to be, because we need to know that in order to allocate memory. And then if that fails, we can test that with a macro. We'll be nice. We'll throw a runtime error because we're supposed to use exceptions. Then we'll request that we want, whatever the original format was, we want RGBA, so ask the library to do conversion for us. We'll allocate the necessary size. They have another macro, thanks C, to get the size in bytes. And then we'll call a finish read function to actually decompress the image and write in the red, green, blue alpha values with various parameters there. If that fails, again, we need to throw. And if it succeeds, that's cool. We can go upload our texture and have fun with it. And then we're done, so the API tells us that we need to call ping image free. So what's wrong with this code? Well, the problem is this ping image free at the bottom. The point of this example is that resource management comes in many forms. We like to bash on new and delete all the time because it's so simple to put in slides, and it is the one that you'll see most of the time. But anytime you acquire a resource from the system and you have to give it back, especially when working with a C library, that is a candidate for the exact same things that we wrap new and delete for. So this is bad because if an exception is thrown, we'll go leak. The fix, and here's the simplest minimal possible fix, is to go use boost scope exit or your favorite scope exit library and say, okay, as soon as we construct or put this C plain old data struct on the stack and initialize it, that's all no fail, we would like to construct a temporary object on the stack whose destructor will free the thing. It'll call ping image free. We go check the API. We make sure it's safe to call as soon as we've mem set the thing and scribbled in the ping image version. Yes, it is safe. So by putting that destructor at the earliest possible point in our program, we're guaranteed that whether we succeed or fail, we'll release our resources. Essentially, what I'm trying to show here is that the compiler knows all the code paths that can be taken through this function. There's the successful code path that we as humans immediately see. You just blast through the end function, you're done. But there's also failure code paths. Every time we throw an exception or we try to construct a vector and that throws an exception because we can't allocate, say, 4 billion bytes of memory because the ping's dimensions lied to us. Or we try to go upload a texture and something happens there, or maybe we're sending it over the network and something happens. Any of those failure paths, we really don't want to leak this opaque ping image struct because it's probably allocated memory, acquired handles, who knows what it's doing. They told us to call ping image free on it, and if we don't, that's bad. What if we're being called in a server program in a tight loop and we're leaking lots of these, or maybe just one per day? That's not good. The compiler knows when to get rid of this stuff, but this is not ideal. If we're going to be working with this library a lot, there's actually a skeleton here, and this is one of the things I would like to show you how to see. Ideally, we would encapsulate this code. What I've highlighted here, and I had to use 4 different colors, is that the stuff in teal, that's really a constructor. We're constructing this handle thing to talk to the library, and that's actually no fail. And then the thing in blue, which is being taken care of by a scope exit right now, that's a destructor. That is going to release this resource we've acquired from the libping library. And the things that are highlighted in purple and pink, these are member functions. You can even see the this pointer there, except it's a C API. It doesn't have this. So it has to pass around address image all the time. We have C++. We can do better. We can do simpler. So if we're going to be doing this a whole bunch of times, compressing, decompressing images, we'd want to write a wrapper class to package this so we can simply construct some handle thing and then say, okay, begin read, and then construct a vector of the right size, and then finish read, and then we're done. We don't need to worry about leaking. We don't need to write all of this boilerplate. So this is a pattern that's going to show up time and time again when you work with libraries that I've never seen before. This is just one example that I've run into. Okay, so let's go back to simple new, delete, shared putter, very simple examples. I try to be as realistic as possible, but if the whole talk were filled with examples with libraries like that, I'd have time for like maybe 3 of them. Okay, so here I've got a relatively artificial example. Some function f taking a const shared putter x reference and then some other vector, const vector ref. And I would like to use initializer lists from C++11 and construct a temporary vector of 11, 22, 33. Here, the compiler will construct the temporary for me, and I don't need to keep it around, so that's totally cool. And I would also like to new up an X, and I don't have one right now, so I'm going to construct a temporary shared putter. So what's wrong with this code? Anybody see? Raise your hands. Who thinks that I should just nuke the shared putter X, like I was in the previous slides? OK, fewer hands. Excellent, because that is wrong. You cannot simply nuke the shared putter X there, because shared putter has an explicit constructor from raw pointer. It's trying to be very careful about when it acquires and releases ownership. So if you just simply try to pass new xargs, that won't even compile. So that's not the fix. The problem here is that we said plain new. And you may have heard of this. I think actually maybe 90% of you have heard of this. This is the classic unnamed smart pointer leak. C++ has this rule that's actually cool in many ways, but inconvenient in this case, that the order of evaluation of function arguments is in general unspecified. The compiler is totally free to say, OK, I'm going to new xargs. Oh, and then I'm going to go construct a temporary vector. OK, and then I'm going to go construct the shared putter and then go call the function. That's actually totally valid and permitted, even if I'm not aware of any compilers that do that. But if that happens, and we new up the x, and then we try to construct the vector, and that fails, either because the vector can't allocate memory or whatever the vector's elements are. In this case, they're int, but maybe they have constructors. If they throw, then we leak the x object because it has not yet been handed off to a shared putter. The problem is that the compiler is just evaluating these functions in any order, and it doesn't know, because we didn't say, that we would really like to pass ownership of x to the shared putter without any interleaving function calls. So the fix here is to simply call make shared. Not only is this more efficient because it avoids storing extra information like we saw last year, but also it's less typing and it's exception safe. No matter in which order these arguments are evaluated, it will not leak, because the construction of the shared putter and the new x are packaged together in a single function. If you read through C++'s rules going back to 98, this is strongly leak resistant, which is very convenient. OK, so now a more complicated example leading into a new feature. OK, so I've been, and actually several of the talks before me have just been hammering on this point. You should use destructors to manage resources. You should not have, raw pointers, all that. So imagine a programmer says, OK, I'm going to manage my resources with a destructor, but I need two of them. OK, so I'll write a wrapper class. I'm being good. I'm going to write a wrapper class that stores some resources, A and B. I don't know what they are. So we've got an A star member underscore A, B star member underscore B, and I need to construct them from some integers or arguments x and y. So I'm going to have these pointers. My constructor is going to carefully null them out using null putter, and then I'm going to new up my objects. And then the destructor is going to be very careful. It's going to delete them in reverse order, so that's nice. And we know that free and delete are no ops for null putter. So if for some reason they're called when these pointers are null, then I'm not going to crash or anything, and that's cool, right? It's cool? OK. What's wrong with this code? Who sees it? OK. What's wrong is that I've said new and delete in the constructor and destructor in this pattern. And the problem is not like unspecified order of evaluation or anything. The problem is that this is a rule going back to C++98 for very good reasons. If an object is never born, it can never die. If an object's constructor does not proceed to completion, to success, then the language, it doesn't know that the object's invariants have been established. So it does not know that the destructor is safe to invoke. In fact, maybe it's got garbage data, or the pointers haven't been set up right, and invoking the destructor could crash. So the rule is that if a constructor throws, the destructor will not be invoked. So if I new up my A and that succeeds, and then I try to new up my B, and either I can't get memory or B's constructor decides to throw, then the destructor of two resources here will not be invoked. I just leak my A, despite my attempts to be good and manage it in a destructor, because I was trying to do too much work. So the best fix is to use individual smart pointers. In this case, I'm showing unique putter and make unique, because C++ does have a rule that when a constructor exits with an exception, the destructor will not be invoked. However, all of its fully constructed data members and base class subobjects will be destroyed in the reverse order of their destruction. So in this example, if the construction of B throws, then two resources won't be destroyed, but its fully constructed member underscore A will. And unique putter has a destructor, so we'll free the A and everything is good. And you'll notice it's actually less typing. It's more elegant. I didn't even need to define a destructor because the implicitly generated one is okay for my purposes. By the way, just because I'm depicting member initializer lists here, that's not the key here. I could simply default construct my members and then say member underscore A equals make unique. That's totally cool. Some people prefer one or the other, but that either way is exception safe. And also, if you want or need to use shared putter, that's also okay. The key is the smart pointer, not necessarily unique putter. In fact, I personally prefer using shared putter. I'll get to the questions at the end. I need to blast through this at like 30% light speed, like I said. Now, I want to introduce something, but I don't want to say that it's good. In this case, there is another way. If you really, really want your new and delete, using C++14, you can get it with just a little tweak. So here I'm demonstrating a new feature. I've still got my A star and B star. The destructor still deletes in reverse order. But instead, I have a default constructor. And you can make it private. You could make a tag type so that nobody else can invoke it. In this case, it's just the default constructor that nulls out the pointers. Then you have your real public constructor that takes the ints or whatever. And then it says colon to resources, and then it says what it said before. What this is a C++11 delegating constructor. You can have constructors call each other now. This is actually very useful in other contexts. But in this case, what it means is that the two resources constructor from two ints will delegate to the default constructor, null out the pointers, and then execute its body essentially as a normal function call, newing up the A and newing up the B. The standard actually says that this will not leak. There's a whole rule here, and this is actually very important. It says once you've got a bunch of delegating constructors, because you can have a whole chain of these things, but once you get up to the first one that executes, or the first one that runs to completion, the non-delegating constructor, once that has completed, the object is considered fully constructed. Its invariants have been established. So at that point, if anything throws, the destructor will be invoked because the invariants have been established by at least one constructor, even if more have come in and tried to do more work. So code like this is actually safe. However, just because you can use this rule and I'm showing it to you doesn't mean you should go off and use it. I've used this in my own code, and I don't know if I felt good about it. It was certainly convenient. But I'm just so aware of the problems of raw pointers that even when encapsulated like this, I don't know. I'm just mentioning it in case anybody else starts telling you to use it. If you do, think carefully. So my recommendations, and these are very common recommendations. New and delete and other raw resource management, they are radioactive. You should be using smart pointers as much as possible. Make shared, make unique. The only times you ever want to use new and delete are when writing fundamental resource managers, like say trees or something, or when writing extremely high performance code and you absolutely cannot take overheads. Actually, make unique has virtually zero overhead, so usually it's appropriate even in ultra high performance code. Similarly, new array and delete array, they're also radioactive. Use vector, or if you're storing characters, use string. Like, never use these things, except in high performance code, blah, blah, blah. I'm actually less sympathetic to those, because vector is just so awesome. Come on. I'm not a big fan of unique putter T bracket bracket, but you can use that too if you want. It'll release. In general, manual resource management is radioactive. At the very least, you should be using a scope exit library like I depicted. Your company may have your own. Or ideally, if you're going to be using these things over and over, write little wrapper classes. Yes, you got to write a little wrapper class, but if you're going to use it over and over, that's easier than always remembering to write a scope card. As I like to say, the needs of the many uses outweigh the needs of the few or the one library implementer. So when you're writing these automatic resource managers, ideally you should have one resource manager acquire and release just one resource and do nothing else, because we've seen if that constructor throws, then you're going to go leak your resource. If you really need to do more work or require multiple resources, remember the gotcha and write it very carefully, whether using try catches or using this delegating constructor trick that I showed you. And just because I'm saying radioactive, it doesn't mean it's always evil. It just means that it's potentially dangerous and it should be shielded, like heavy lead shielding, containment, encapsulation, all that stuff. Because the compiler knows, like if you look at C++, yeah, it's a bunch of rules, but there's a very strong theme running throughout the language, and that it wants things to be managed by objects, and that it is very careful about destroying those objects in the right order. When you exit from a block, objects are destroyed in reverse order. When you destroy array, all the elements are destroyed. And when you throw an exception, things are destroyed on the stack, including members and base classes, all that stuff. When you write code that hooks into the destructor machinery, you're getting the compiler to take advantage of its lifetime information, so you don't need to go write C-style code of, okay, if fail, go to error, if we got this thing, then free. We've all seen that code. It's awful. It's also not efficient. All those branches are not cool. Exceptions on modern machines like x64, they're typically implemented with a table-based approach that have zero overhead in the non-throwing case. Use that machinery. Okay, so value categories, which is less familiar to many programmers. Certainly when we first got R value references, I had like a 3-day raging headache trying to figure out what these L value and R value things are. So imagine, let's go back, simple C++98 example. We're taught from an early age as programmers, in kindergarten, that unintentionally modifying state, it's very bad, especially if you go give some object to a function. What if it goes scribbles in it and we're not aware that it's modifying our state, especially if it's like global? That's like really bad. So we want to start putting const everywhere we can. And I'm a huge fan of this. But should we say const everywhere we can? Here we've got an example. Imagine I've got some function meow that returns a temporary string, returns a temporary string also saying meow. I would like to forbid a certain kind of code. C++98 and beyond actually permit you to say meow.append per. This is calling a modifying member function on a temporary. This is actually kind of strange because C++98 and beyond forbid passing temporary strings to functions taking modifiable, say, string ref. That's forbidden because such a function would try to write something and expect that its writes would be visible later. Yet if it's writing to a temporary string, that's going to be dropped on the floor at the end of the full expression. Probably not what the programmer intended. So that's banned for good reason, and VC is extraordinarily evil for permitting it as an extension. We should rip it out someday. Yet C++98 permits these modifying member functions to be invoked on temporaries. Maybe that's squirrely. Maybe we want to lock that down and return by const value. That definitely forbids this. What's wrong with that? Does anybody see? Okay, fewer hands. Okay, that's what I was expecting. The problem with this is in C++11, it inhibits move semantics. Because if you return a temporary string by const value, then it's a const R value. It can't be passed to a modifiable string ref. Yeah, it's a temporary. The compiler can see that. But you also said it was const. Const means you can't scribble into the bits, like, say, copying its pointer and then nulling it out. So yeah, you're locking down saying meow.append, but you're also inhibiting move semantics, which is the major efficiency improvement in C++11. We will probably never get such an improvement because although C++98 is extremely efficient, it had one minor sin, and that's that it liked to copy objects a little too much because it combines C's love of value semantics with C++ objects that are not trivial to copy always. Move semantics solves that problem. So when you say things like const string and you're inhibiting move semantics, you're degrading the performance that you would otherwise get. I mean, why are you even using C++ in that case? So if you just return string by modifiable value, or any object by modifiable value, you get move semantics, and it's actually not important to prevent modifiable member functions from being called on such temporaries. C++ permits that because it's not actually evil. Yes, you're modifying a temporary, but such functions usually return the object again or a reference to it. And it's obvious that, yes, you've just modified in place, but you're still going to do something with it. OK, so here's another example where I'm upgraded to C++11. I've heard that move semantics are awesome. I should use them all the time. So I'm returning a string by value. And I've got a string bret. It's a local variable. I need to do complicated stuff to it, not just a single line. And then I know that in general, L values are named expressions, and I cannot copy from them, or I cannot move from them, because that would scribble null pointers into them, and it would be obvious. So if I say return move, I'm trying to move it out. The problem with this, does anybody see? I actually didn't learn this until, I think, BoostCon 2012. The problem with this, actually, is that it inhibits the return value optimization and the named return value optimization. In this case, it's the NRVO because it has a name, because I've said move. The NRVO is very, very specific. It's when you return a local variable of the same type then the compiler can skip any copying and just directly construct the variable in its final destination. As soon as you put a function call in there, the NRVO is disabled. You just can't do that because even though the function is essentially a no-op, it's a cast, the compiler doesn't know. It can't allow arbitrary functions to take advantage of that optimization. And in fact, if the RVO and the NRVO are not applicable, C++11 steps in with a rule that says, OK, in this situation where you would get the opportunity for the NRVO, and for whatever reason you can't actually activate it, you are required to activate move semantics even though it's an L value. And this is actually tricky. Because it's a local variable and you're returning, the compiler knows it's about to be destroyed. So even though it has a name, it's not going to have a name for very much longer. And yeah, we can just steal its brains because nobody's going to notice when we return from the function. In this one case, the standard says treat that L value as an R value. So you're already going to be efficient. Basically, if the NRVO happens, no instructions, optimal. If it can't, for example, for an assignment, then you get move semantics, which is almost optimal. They work together. They don't conflict. So don't say move there. Now here's a related example. Here I've got a couple types that are interconvertible. Here I've got a tuple of string, meow is returning that. And I've got a local variable of type pair string, and then I do some stuff. And then I want to move it out, so I say move p. Who sees what's wrong with this? It is not wrong. In this case, this is the one example where the code is not wrong. I got you. In this case, the types are different. It is not a candidate for the NRVO. This is a normal construction from an L value, and the compiler will copy unless you say move. Now, this is actually pretty obscure. I had to think pretty hard until I could come up with plausible types that would be different. And even then, it's really contrived. Why not just have a local tuple there? But if this situation arises, just be aware the NRVO is really specific about the types being the same. And if they're not, there's some bit about CV qualifiers. But if they're substantially not the same, then you should say move. Consult your resident language lawyer. OK, so more R-value references. We hear about R-value references. This is like R-value references 101. We have a local string s. We do stuff to it. Then we try to return s. But here, instead of saying like move or anything, we want to return an R-value reference. So we say string ref meow. And in fact, this code, my brain is now saying, will not compile because it doesn't activate that R-value thing. The user would really try to say return move s. That would compile. Yet it's still wrong with that. Who sees what's wrong with this? This one is simple again. OK. The problem here, let me ask another question. What if I wrote this in C++98? This will also compile, where I say string s stuff, return s, and I return a string ref. Who sees what's wrong with that? The problem is you're returning a reference to a local variable, which is about to be destroyed. Just because we granted R-value references in C++11 doesn't change this rule. In fact, there's a whole rule in C++11, which I quoted here. It's actually not that verbose. It just says that L-value references, the old style, and R-value references, they're collectively called references, and except when otherwise described, they behave the same. They share an intrinsic referenceness. And the fact that you can't return references to local variables has not changed. So you should not do this. Just return your string by value, and you'll get the NRVO and move semantics, like I mentioned. OK, so let's say the users learn not to do that, but they're still really intent on returning R-value references. The standardization committee did this. This is not a newbie mistake. Here I've got a join example. Yeah, I know, seriously. We almost shipped this. So we've got a join function. It takes an R-value string, and it wants to append some consecure star, but it wants to do something extra. It wants to add a comma. So I can't just use the standard library for this. So I'm going to do a couple chained appends, and then I'm going to move it out. That move is necessary because the NRVO doesn't activate here. The function call is returning a string ref. And I want to say string ref. This actually compiles. And this actually works. And it's actually efficient, like all the time. Like so much so that you could vote it into a C++OX working paper and have lots of experts not notice the problem. Yet there is a problem. Who sees what's wrong? OK, almost nobody. The problem here is very subtle and extremely bad if this join function is instead called operator plus, which is what it was in the standard. Imagine that you have a meow function. At this point, the user has just given up. They say, OK, I'm going to return by value, whatever. Stop hissing at me. And then somebody calls join with that temporary string returned by meow and then whatever string literal. And then they try to bind it to a const string ref. Many programmers actually go through their whole careers, I'm surprised, without ever seeing this, but C++ 98 lets you bind a const string ref to a temporary. And if it's directly bound to a temporary object, such as return by meow directly, the lifetime of the temporary, which would ordinarily be destroyed at the semicolon at the end of the full expression, instead it is prolonged for the lifetime of the reference. But that's very specific to directly binding to a temporary. Any intervening function calls, and the compiler cannot see that. And if you introduce intervening function calls, then the temporary is destroyed at the semicolon. So in this case, the temporary return my meow, which has been appended to in place, is destroyed at the semicolon. R refers to a destroyed temporary, and the next time you try to access it, you'll get undefined behavior. That's not good. Instead, if you return your string by value, you still get the benefits of move semantics. You take a temporary string, you append in place, potentially reallocating in geometric fashion, and then you move its guts into a fresh temporary. So you do get a move into a fresh temporary, but at no point are you gratuitously copying the string's data, which is what we want to avoid. This is the exact same fix that was applied to C++ 11 before it shipped, thankfully, and we actually managed to catch it in the library as well. So recommendations. If you see anybody returning by const value, stop them before they injure themselves and you. Just never do this. It doesn't prevent anything useful. And in fact, for built-ins, if the compiler sees you returning a built-in like an int by value, it immediately erases that. It's like, wow, and this is the standard ease. Wow, a CV qualified, PR value of non-class, non-array type. I can't have that, and it just wipes it out. Like literally, const value. Never do that. It inhibits move semantics. And also, in this pattern, when you return a local x by the exact same type, don't say move, because the NRVO and move semantics work hand in hand. They're not competing. They're covering for each other. And then finally, just don't return by R value reference. Like I said, even the committee got burned. There are legitimate cases where this is possible, but they're very rare and they're very complicated to reason about. And I don't believe that they often occur in ordinary code or even library code that often. I put a few examples there. Forward and move are powered by this. Declval, which isn't even implemented, it's just a declaration. And get for R value reference tuples. I just did a quick scan of the standard library. These are extremely obscure. Like I have to sit down for like 20 minutes and figure out what get for R value tuples is doing, and that yes, returning an R value reference is desirable. In general, don't return by R value reference. It's okay as a parameter, but not as a return type. Okay, so types. Let's go back a little simple to C++ 98. This example actually is an example of user code that doesn't work, and it leads into this don't help the compiler theme. So here I've got an example of some function, meow, taking a const pair ref of some A and B star. We don't care what A is. And then some struct C that's constructible from a D star. And I'm used to saying 0 or null for my null pointers. In fact, I'm surprised. Some programmers in C++ think that 0 is preferable instead of null, probably because C null was like horrible. And so they always say 0. And yet these things will not compile. So it's not like silent bad code. It's just, it won't compile at all. Who sees why this won't compile? Who can do template argument deduction in their head? Yes, of course you can, Jonathan. I would hope so. The problem here is that 0's type is int. You feed it to a template, and it says, wow, you got an int there, cool. So make pair A0, that returns a pair of A and int. And then int is not convertible to B star. That's bad. Or make shared, that's going to call make shared of int ref ref. And int ref ref is not convertible to D star. There's this rule in C++ 98 and in C that the literal 0 is a null pointer constant. It can be converted to a raw pointer. But that's specific to the literal. The type is wrong. The type is int. As I say, this is an abomination that exists outside of the type system. That's like a horror from beyond space-time. And null is equally bad, because it's a macro. In C++ 11, we have the right way to do this. If we use the constant null putter, that has the right type. And you'll get a pair of A and null putter T, and null putter is convertible to any raw pointer or pointer to member for you library devs in the audience. And it just does the right thing. It works with templates. We really should have had this in C++ 98. It's so simple. But we should have had static assert first. So with make pair, users ran into this whole zero problem, and sometimes they're like, oh, instead of writing null putter, maybe because they were doing this during C++ 98 and they didn't have null putter yet, they said, oh, I can just pass explicit template arguments. So often you'll see code like this, here just A and B or whatever types. I see this. I am so surprised because I would never write such a thing. Of course, I also maintain a standard library, so I know what it's doing. I see this regularly, that users say make pair AB, A comma B, where A and B are the types and A and B are the variables. This is wrong. Does anybody know why it's wrong? Only a few hands. OK, so I would expect the hand count would go down during the talk. Excellent. Getting into new territory. The problem with this is that it does work in C++ 03. In C++ 03, this is make pair signature, so you can pass A and B there, and as long as you're correct about the types, everything's cool. The problem is that in C++ 11, the signature changed. It was sprinkled with R-value reference magic dust. It is now taking T1 ref ref and T2 ref ref. So if you pass in the types explicitly, capital A and capital B, the compiler forms the signature make pair taking A ref ref and B ref ref. Those R value references will not bind to L values for safety, and you fail to compile. And then the user files a bug report saying, hey, you stupid maintainers, you broke my code. And we resolve it as by design, saying, hey, you stupid user, don't do that. Though in more diplomatic language. So the worst part about this whole thing is that passing explicit template arguments to make pair, not only does it break in C++ 11, it defeats the entire purpose of make pair. The whole purpose of make pair is for template argument deduction. So you don't have to say pair of AB all the time. You just call make pair without arguments, and it gets the right thing. In this case, it'll do move semantics in 11, and that's awesome. Every once in a while, you do need to explicitly change the types. Maybe you got like ints and you need shorts or longs. In that case, you should say pair of X and Y constructed from different types, A and B. And that's mentioning a class name, not a function name. In no case should you ever pass explicit template arguments to make pair. It's awful. OK, so that's one way. This is one of three. One way that explicit template arguments can blow up. Here's a second way, and this one is different. So here I've got a transform call. I don't even care what the range are. Two ranges. I'm zipping them together and getting the max. Apparently, these are ranges of ints. I'm getting the maximum int from each range and writing it into a third range, which might be one of the originals. And yet, max is a function template. So if I just say max by itself, it'll fail to compile. The compiler will say, hey, I don't know which signature of max you want. So the user has helpfully said, OK, I know which max you want. You want the max for int. This compiles in C++ 98. So it's good code, right? So here is the declaration in C++ 98. There's another overload for comparator. We don't care about that one. And the overload that the user wants takes const tref and const tref and returns const tref. So does anybody know why this fails in 11? 0 hands that I see. So the problem here is not that the signature changed in C++ 11, but that a signature was added. A totally different signature, max for an initializer list, because the committee wanted you to be able to say max of brace 11, 22, 33, brace paren, and get the maximum value. That's actually pretty cool. This signature was added, and it doesn't compete. It's not ambiguous in terms of overload resolution with the 2-argument version. It's not even the same number of arguments. But it is a single template argument overload. And when you say something like max of int in C++ 11, the compiler says, oh, I could form the signature max taking constant ref, returning constant ref. And I could form the signature max taking initializer list of int. Now, because there's 2 signatures, the compiler, again, doesn't know which one you want, and it's ambiguous. All because a completely independent overload was added that just happened to have a single template argument. This is bad. Unfortunately, the solution here is a little verbose, but it's a good solution. You just shouldn't use explicit template arguments. The solution is to use a static cast. If you say static cast 2, pointer to function taking constant ref, returning constant ref, then you're very unambiguous. I know it looks horrible, but yeah, it's horrible. But I'll show you. I've got a bonus slide that makes it even worse if you try to use a lambda. What this goes through, this actually goes through different language in the standard. This actually activates template argument deduction. This is the one example that I'm aware of in the standard where information essentially flows backwards, where the context of something, in this case, an overloaded or templated function name, can disambiguate something that would otherwise be ambiguous. In this case, you have max, and by itself that's ambiguous, or address max, same thing. But when you static cast it to a particular pointer or assign it or pass it to a function with a fixed signature, the compiler says, oh, I'll do template argument deduction and figure out, or overload resolution, and figure out which one you want. This goes through that mechanism, and it's immune to extra overloads being added. Or you can use a lambda, but I'll show you in a bonus slide why lambdas actually aren't that awesome. This is just a hard problem. We haven't really solved it yet. Finally, there's a third way that I've seen that explicit template arguments can explode. In this case, somebody's got, and this actually hooks into the RAND talk I'm giving on Friday, somebody's got a range apparently of pointers to uint32ts, not important, and they've got a generator of Mercian twister type, that's a type def, and they would like to run that generator in place. The standard says, and this is awesome, that STL maintainers are allowed to copy function objects freely. In general, we maintainers like it when we're allowed to do cool things and the users aren't allowed to complain. The user doesn't want us to copy the function object. So they say, OK, instead of taking it by value, which is what would happen if I use template argument deduction, and that would run a copy of the generator and not affect the original. So the next time I run the original, I would get the same random numbers, and that would be bad. Instead, I'm going to say, hey, take it by reference. I see users doing this. I've got bug reports saying that we should work with this. And this works for some implementations, I suspect like GCC and probably libc++. Does not and has never worked with VC's implementation going back at least to like 2005. Does anybody know why this doesn't work? OK, nobody reads the standard library headers for fun. I'm disappointed. So the reason why is that the public signature of generate takes the generator by value. And this is the one that the users are trying to affect. Here I've color-coded things. So the user passes a reference as the type of the generator, and we take by reference. But then we go do some maybe debugging checks or centralization or whatever. And then we call a helper function. And our helper function just happens to be called _capital generate, because that's a name that users can't say. And then we pass G. That helper function has the same signature as the public function. We just repeat it. And then we go do our stuff. The problem is that we're calling the helper function, as we're permitted to by the standard, with template argument deduction. So maybe the user injected explicit template arguments to the public overload, but then we just drop that on the floor. And we use template argument deduction in the call to the helper function. Standard lets us do this, so the user's wrong, for sure. And in fact, there's a better way to do this. They don't need to write bracket uint32t. Ugh. Instead, they can control the type that's being fed to the function and use template argument deduction. If they simply call generate first last and then use C++11's reference wrapper, there's a helper function called ref. You call ref with some object and it returns a reference wrapper of t. That thing really stores a pointer, but it pretends to be a reference, except that it's assignable and copyable, so you can actually put it in containers and stuff. In this case, this will pass a reference wrapper to the generator and invoke the original one in place. And the reference wrapper can be copied, but who cares? It's just a non-owning raw pointer. And it's less typing. It's nice, and it works, with all implementations, which is definitely a redeeming quality. So that's the third way I have seen that explicit template arguments can explode. There's probably more. I just haven't run into them yet. Actually, there is one more, but it's very obscure. So what I recommend is always use null putter. Sometimes there are guidelines that are like, yeah, maybe you should do this, except in this other case. But zero null, they're just abominations. Don't write them. The only excuse I can ever imagine for writing zero null is if you're writing a dual mode C and C++ header, in which case you have my pity. That's just horrible. But in C++, just never say null. Always say null putter. It's not that the type says what it is. It's not that the name says what it is. It's that it has the right type, null putter t. It works with the type system rather than being the special rule that depends on the literalness of zero. It also locks down various horrible things like initializing ints with null putter. People do that all the time. They're just horrible people. Within Visual Studio's own source base, I could not believe. We were confused. We thought that we had to change the macro null to be null putter. I tried to do that. We found like 1,000 explosions and tried to fix most of them before we realized, wait, the standard doesn't require that, and we backed it out. Then as for all of these cases where explicit template arguments explode, the theme is that you should rely on template argument deduction. Just like C++ wants you to manage resources with destructors, C++, the core language in the standard library, they really, really want you to call algorithms and other functions with template argument deduction. This is the intended way that they're supposed to be used. If you want to change how they work, like we saw with the generate example where we want to change how it takes the function object, you should control the types of the inputs and allow that to flow through the rest of the function, and overload resolution, all that stuff. You can also change the value categories by saying move. And in general, I've seen this over and over. Just try to avoid explicit template arguments because there's so many ways they can explode, and there's usually better alternatives. And the exception, of course, is when they're required. So for example, forward TT, its whole purpose in life is to put the type back in. You can't call it without an explicit template argument. Or make shared, it needs to know what type to construct so you always have to pass t. But like make shared has other arguments for the constructor. Those should be used with they should be used with template argument deduction. So in the case where I'm calling make shared of t with ABC, the compiler knows the types of A, B, and C and whether they're L values or R values. So I should not try to be helpful and say, hey, compiler, those types are capital A, capital B, capital C, because I'm going to run into the same sort of problems. I'm writing unnecessary code. I shouldn't do that. Okay, so my final example, it goes all the way back to C++98. Thanks to the brilliant design of the STL by Stepanov, its algorithms and its containers are customizable with functors. And a functor is just anything that's callable like a function. So this is sort of functor 101. I'll go through it fast. So obviously functions themselves are callable. Other things are too. For example, function pointers. C says, hey, you're trying to call a function pointer? Yeah, I'll just automatically dereference it. What else could you be doing? And that's actually quite convenient. Or function objects. They're classes, but they overload the operator paren. Or lambdas, which are just a convenient way to stamp out the classes. Some things aren't callable with that syntax, though. Pointers to member functions are callable with weird syntax. There's adapters for that in the standard library. And also, and importantly, operators use special syntax, x less than y, or x plus y. You can't pass operator less than to algorithm. For example, even if it's for class type, maybe it's a member instead of a non-member function. So you can't simply say operator address of and some horrible static cast or something. And if it's a built-in, you can't even form a function pointer to an operator less than, taking built-ins. They exist only for the purposes of overload resolution. So the STL back in 98 provided less of t. And this is just a very simple wrapper class whose sole purpose in life is to adapt the functor syntax that the STL algorithms want to the operator syntax that we want to usually use. And you might be saying, okay, we got C++ 11 lambdas, and they're even more awesome in C++ 14. We don't need stupid wrappers like less, just like we don't need bind first and bind second and all those horrors that we've heard of. But actually, that's not true. In this case, I'm trying to sort a couple elements, and I want to sort them in reverse order. If you look at what you have to type for a lambda, and C++ 14 polymorphic lambdas don't help here. If you try to write a lambda, it ends up being much more verbose than the dedicated special purpose operator functor. So although they're not general purpose, in their very limited domain, they are still useful. So it's not like we should just throw them away. Also, if you want to customize a container's behavior, putting the type in there is much more convenient than trying to use a lambda, and it doesn't work with VC because we got a bug that we need to fix. Yeah, we need to fix that one. Also, these operator functors, they're cool. And they were extremely useful in C++98. They're not bad at all, but they're limited. For example, somebody writes a vector of u and 32t, and then they try to sort it by greater u and 32t. Here this is using student h's, fixed length type def, or some user type def, whatever. I just wanted to be very explicit about the size here. So this is all good. Who can guess what would go wrong here? The highlighting? Does the highlighting help? OK, somebody has guessed. The problem here is what if the code is updated inconsistently? For example, somebody modifies the vector. Maybe they need larger IDs or something. And they say, OK, I need a vector of u and 64t. But then they missed the sort call. Maybe it's in some other translation unit. Maybe their IDE lookup didn't find it, or whatever. Or maybe it was a type def and their grep didn't find it. In this case, it will compile. The standard requires it to compile unless you're compiling with warnings and errors. And it'll truncate. The greater functor takes u and 32t's, and it's going to be passed u and 64t's from the container, and it's going to truncate and compare them. That's not going to do what you expect. If you're lucky, you'll get a warning. Some compilers, for example, VC, they actually do warn here by default. Not all of them. I won't name the ones that don't. But it's not just like a compiler thing. There's an equally dangerous case. Imagine that you've got a vector of int 32t, so it's signed. It can be negative. And what if you pass that to a greater of u and 32t? In this case, it's equally bad, because negative numbers will be converted to large unsigned numbers, which compare differently. And then the small unsigned number, or the small positive numbers won't be have their values changed. So the conversion will start returning different answers. Equally dangerous, but compilers actually consider sign conversion warnings to be more noisy, and they warn about them less. In fact, it was extremely hard for me to get any compilers to warn about that case. So this is bad, the fact that we're repeating this type information that the compiler already knows in some sense. Here's some more problems. So all of the operator functors, they all have the same skeletal structure. Here I've indented it sort of weird so I can show you how they all share the same structure. This is what they look like. They take const tref, and they return t by value or bool. So imagine I've got a units library and I want to use this with the STL, maybe in a transform. But if I try to pass, say, watts times seconds to multiplies, that won't work because those are different types and they actually return a third different type, joules. And yet the multiplies functor insists on having the types all be the same. Or imagine that I'm comparing things that the STL will work with, but inefficiently. If I call greater of std string with a const char star on one side and a std string on the other, because the signature takes const string ref, that'll construct a temporary. Because like I said, C++ is all too willing to construct temporaries for you. It wants to help you. It wants to say, hey, you wrote some code. I'm going to compile it for you. Yes, I'm a good compiler. And yet that's inefficient because we could just compare the thing in place. Or even if the types are the same, it can still be undesirable. For example, you call plus of std string, and you give it a string L value and a string R value. We pass that string R value to const string ref, and at that point, we've applied constantness and L valueness to it, so we can't steal from it because we said, hey, we're not going to modify this thing. So we get an unnecessary copy, all because the signature took this particular form. So in C++ 14, this is actually a proposal I wrote that was accepted. There's what I call transparent operator functors, and they look sort of strange at first. They were implemented or designed in a backwards compatible manner. Basically, C++ 98 took all the good names. I really wanted to use the names lowercase less and lowercase greater and all that stuff. Unfortunately, you really cannot overload the name of a class template like that. You could put in a different namespace, but then you'd run into the same problems as soon as somebody says a using directive or using declaration. The committee violently hated the idea of saying capital L less. I asked for a straw poll. They were just strongly against. They hate the capital letters. But we can add an explicit template argument. Default template argument. I hate the explicit ones. Turns out void was totally illegal before because you can't form a const reference to void. So we can hijack the meaning of less of void and make that special. So now all the operator functors have a default template argument of void and explicit specializations. Void is just meaningless. They are essentially non-templates. They've lost their templateness, and instead they have a templated function called operator, like we saw in Sean Parent's presentation. In this case, it takes a sort of unusual looking form, but it basically takes its arguments by perfect forwarding, allowing them to be different types, and then it returns by perfect returning using this decal type thing. This manages to get the exact result in all the possible cases. I could walk through it. Basically, if you're library dev, you can see what it does. If you're not a library dev, you don't really need to know what it does. It just always works, and it doesn't mess with the types coming in. So usage of it actually looks really simple. All you do is you omit the type information that you would have said to less or greater or plus or whatever, and you write an empty diamond. It's 2 more characters than ideal. Here I've got a set that I want to sort in reverse order, and then I want to transform some const char stars and some std strings and plus them together to concatenate. Remember how I said that type information controls what happens? In this case, the types const char star and std string, along with the type of the plus diamond functor, controls what operation happens. It's all inlined away. And I don't need to repeat the fact that I'm working on std strings or const char stars or any of that. So this emits optimal code gen. I get full inlining because all this stuff is very simple, and the compiler doesn't construct unnecessary temporaries. I get move semantics if necessary, and I did less typing. It's just a win all around. So as I originally mentioned, what I wanted to show through all of these examples of stuff not to do, new features, I know it's kind of mind-bending, is a way to look at code. So if you hadn't gone through this talk and you'd never seen like RVI references before, you would see, okay, you got some template there and references, okay, that's like C++ 98. And then the thing at the bottom looks like really complicated. And I know it is. It's actually simpler in C++ 14, but that's basically the signature. But what I see is different. I don't see like ampersands coming out of everywhere. What I see is that in the first C++ 98 form, where the template parameter belongs to the class, the user is providing the type to the standard library too early. That's when they're forming the type of the functor, and that's before the call has happened, before the compiler knows the types of the arguments and the value categories of the arguments that are going to be passed in. Instead, when the class is just a plain old struct or an explicit specialization, and we take by perfect forwarding and then return by perfect returning, the compiler will deduce the types at the right time, using full knowledge of what's being passed in, whether it's L values or R values. So it's not going to get the types wrong. It's not going to introduce unnecessary copies or any of that stuff. Yeah, it allows template argument deduction to do the right thing. So I've been hammering on when not to help the compiler, but of course sometimes you do need to. In your code, with your high-level knowledge of your program, sometimes you need to say, hey, compiler, do this other thing. The most notorious example is casts. I haven't even been hammering on why casts are awful, because we all know why they're awful. Sometimes you do need to. Of course, you should never use ccasts, because those things are awful. You should use static cast and reinterpret cast and all those things when you know, for some high-level reason, that the type system can be briefly ignored. Type system is good, but being able to temporarily suspend its rules and go down to the metal is also a useful ability. Not all casts are evil, it's just overuse and unskilled use of casts is evil. Similarly, moves. You should use them carefully, because if you say move, you might steal from an L value. Are you certain that that's safe? Unintentionally stealing from L values is very bad. I've seen bugs, compiler bugs that have been fixed, where we stole from L values and the IDE crashed because various smart pointers were nulled out for no reason because they were mentioned like twice, and the second mention saw a moved from object. Very bad. In general, when you move from something, you're not only saying, I can move from this, but I'm not going to, in general, care about its state. It's going to be destroyed, it's going to be reassigned to, or for whatever reason, I'm just not going to look at it. In general, you should assume that move from means some unspecified but valid state. A few types guarantee something stronger. For example, shared putter and unique putter guarantee that when they're moved from, they are empty, and they're always empty. But like vector, no such guarantee. Move really is friendly syntax for a cast that modifies the value category. It's just avoiding the need to specify the type again. And finally, and this is sort of a new thing for advanced programmers, they gain the power of enable if, and they just want to use it everywhere. But this is an extremely powerful and dangerous tool. You should really avoid this unless absolutely necessary, because when you say enable if, you're saying, hey, overload resolution, clause 13 of the standard, I'm smarter than you. I know which overload should be selected, and oftentimes that may not be the case. If you are smarter than overload resolution, then use enable if to disambiguate. Otherwise, you should use the more specialized and safer and simpler tools of tag dispatch and static cert, either to select between implementations or to just verify that incoming types are valid. So all of these things, you should be trying to do something different than what the compiler would ordinarily do only when you have high-level knowledge that this is safe. So what I've been trying to show with all these examples of things that are bad and then new features is you should be writing your code in a way that you allow C++'s rules that drive systems to work with your code. These systems, like all the rules about destroying objects as exceptions unwind, destroying members in reverse order, that's a system for acquiring and releasing resources without any garbage collector. No other languages that I have seen have actually solved this problem. You go to people, you explain it to them, you give them the solution. You're like, Strauss-Strip solved this. They're like, no, you need a garbage collector. They are neither necessary nor sufficient because they don't handle non-memory resources. Yeah, end of rant. Also, all these crazy, I know this seems sort of crazy, rules for L values and R values and the whole X value, PR value thing. That's a system for identifying resources in your program that can be stolen instead of copied. In some ways, what I view this as is solving the alias problem. If you've ever looked at compiler optimizations, they are incredibly burdened by the fact that when you have pointers in a program, it's very hard to tell which ones point to things that nobody else can see, so they can go mess with that in a way that the rest of the program won't be affected. What L values and R values, value categories do, is they allow the system to see some objects, some vectors, some strings that the rest of the program can't or has declared that they won't care about, so that its resources can be destructively stolen, which otherwise would not be possible without a Skynet-level compiler. And then finally, this whole type system, which is, I know it's templates and R-value references, but this is another system that allows you to select actions to take at runtime, but at compile time with zero overhead. You could easily imagine a sort algorithm that was customizable using, you derive from a sorter, and then you overload its virtual comparator, and then we're going to invoke the comparator on your elements. I'm sure that's how they did it, back in the 80s. That's like very bad. You're paying all these virtual calls. It's heavyweight. Instead, if you simply give an algorithm a function object, maybe a lambda, and say, here is the behavior, it's sort of behavior crystallized into a little lambda expression to compare objects, that type flows through the template instantiation and stamps out a function with zero overhead. This is extremely useful. You should really use these systems once you're aware with them, and you should not interfere with them, like saying, here, let me help you construct a temporary. Let me tell you what these template arguments are. Like 99.99% of the time, the compiler is better at template argument deduction than you are. Even as a maintainer of the STL, I almost never use explicit template arguments when they're not necessary. And if you try to help the compiler, you will feel pain. The machine cannot cry, but you can. However, if you write your code, to work with these systems, then you can actually write simpler terser code, and you can actually enjoy life rather than having to say, all this very low-level code about unwinding resources. You write very simple code, work with the systems, and you're just done, and you're correct and efficient. So we have apparently 1 minute. I don't know if that's enough time for questions.
Yeah, one question.
OK.
One question. Who hasn't asked a question? Come on, man. STL, ask.
That was like 51 slides. How can you not have questions?
Too much information.
I see a question back there. Oh, yes, you should download the slide deck, which will be available. These are things that I could not fit into the actual presentation, which almost ran over, including something that explained that make pair thing that some people with eagle eyes noticed. Pairs return type is weird for a very good reason. Oh, yeah. Here's the one that shows why lambdas are actually not awesome for that max thing. Here's all the possible lambdas you could write, and they're actually worse than that static cast. It's just no real good solution other than making max a functor with a templated function call operator.
Okay, question here.
Yeah.
Could you scroll to slide 45?
35. I want to go fast. Come on, fast. I have too many little animations. OK, here we go. 35. Yes, generate.
45.
Oh, 45. I went too far. Come on. OK. Oh, here we go. Yeah.
Why we are using error reference, not a const reference as before here?
Oh, yes. That is for perfect forwarding. And this is the plus example. Imagine I call plus with a string L value and a string R value. I want that right-hand argument to be string ref. I want it to be a modifiable R value reference so I can steal its brains using operator plus, which will already do that, and then move it out. If I insisted on taking const tref, then that would apply constness and an L value, and I would not be able to move from it. The perfect forwarding basically says, I'm going to step out of the way. I'm going to do whatever that operator plus does. Because remember, this struct exists only because we cannot say operator plus or like a plus sign. We need an object of a type. But otherwise, we don't want to interfere with its arguments and its return type. And although perfect forwarding and perfect returning are sort of verbose, this is the way to do it in C++ 11. In C++ 14, it's actually not as bad. We can use this cool thing that they just voted in called decal type auto. You'll notice the redundancy here between these expressions. In C++ 11, we have to repeat the expression of the body in the decal type. But with C++ 14, we can just say decal type auto, and that says, hey, decal type of the return expression. It's more elegant. But that's only something for like library implementers. As a user, it doesn't affect you.
Thank you, Stefan.
Cool.
Awesome.